Okay, let's continue from part 1. So here we have the voltage swing from DC swipe from the actual for 741, and this is my reconstructed one. Here side-to-side comparison. So again, DC V in from -10 to 10, expecting a gain of -2, and comparing it to the datasheet, we're still in the range. So the datasheet said should be around plus or minus 14, so we're still in the range. And then let's go into electrical characteristic. First, let's go through input offset voltage. So here, to measure the input offset voltage VOS, we're going to use this schematic, which is same as what we did from lab 1. So here's the equation for calculating that. Not going into too much detail since this has already been done from lab 1. So we're using this equation. We use this setup with a and then we get the value of. So the actual 741 has a value of 9.58 millivolt, which is still a bit higher than maximum. And then on ours is like way higher than what the schematic said, since it's built of BJTs. And then here's the input bias current for the positive terminal. We're going to use this equation with R1 of 100 ohm, R2 of 1 mega ohm, feedback of 1K. And then again, here's the equation from lab 1. We're going to reconstruct the circuit, and then we have a so for the actual 741 is in the range between of the datasheet, and then for ours is 8.4 microamp, which is a lot higher than what it say from the schematic, from the datasheet. And then we want to go to the input offset current. So we're going to use this setup, and here are the equations to calculate the I offset. From the datasheet, the max typical is 2 nanoamp, maximum 20, and then we're using our of 1 mega, and then R2 is equal to R1 parallel of RF, which is 91 kilo. And then here's our value. The actual one has a 7.2 nano, which is still in range. And then our input offset current is close to the actual one, which is good. 7.89 nanoamp. And then common mode rejection. So to do the common mode rejection, we're going to use this setup and then simulate. Since it's a snow day today, school is closed, so I'm not able to simulate this circuit. However, here's the setup. Because there's a limitation maximum of component you can simulate on the student version, and since the lab is closed today, so I don't have the numbers, but here's the setup. With the simulate, we should be able to get the number. And here's the slew rate. Slew rate is described when a waveform is slowed when it's close to the cutoff frequency. So our cutoff is around 33 kilohertz on this setup, on the gain of 2 setup. So here's the formula for calculating the slew rate. And here's the schematic from the book, how we can calculate it, how we can simulate it. So 2 pi times the cutoff frequency, which is 33 kilo, times 2, which is the gain, which is the maximum peak voltage of the signal, So we have 0.4 V per microsecond, which is close to the what the datasheet said. Okay, now we're done with the LM741. We want to move on to the 5-volt version of the CMOS low power op-amp. So here's my design. It's a 3-stage amplifier design. First, we have a input bias at the current bias stage. Here, this is the schematic from the book. I'm reconstructing this on the left side. So this is the input bias. And then on the right hand side, we have a differential amplifier with a current mirror here. So see, this is current mirror getting from this bias circuit. And then here we have another current mirror here as a active low. And then we have a differential amplifier. And then stage 2, we have another just one single CMOS acting as an amplifier. And then this is going to serve as a current supply. And then here we have a compensator. Let's go into detail. First, here's the biasing circuit. Here's the circuit from the book. I'm reconstructing this. In PSplice, I'm not able to configure individual width of each transistor, but has the equation to calculate the reference current, and this can be tuned by this resistor over here. And then here in the second stage, we have the differential input. This is the positive terminal, this is the negative terminal, and then this is the biasing for our circuits. And then we have a current mirror. So Q5, what is it? Q5 is a current source. Q12 is a differential amp. Q3 and Q4 is the current mirror. And then for the output stage, Q6 is a common source transistor, and then Q7 is a current source loading, and then we also have a frequency compensation, Miller compensation, 1 pico. So let's look at the output. I'm using the same setup as I used before. No, sorry, actually I'm using a follower here, 5K and 5K. We expect a gain of -1. So we can see here, peak to peak 40 milli, and we have a inverted signal. And then here we try a -2 gain, 5K and 2.5K. And the red one is the input, the green one is the output. So we have a -2 output, which is working. Frequency response, again, this is the red one is the actual LM741. The green one is my low power version. So we have a similar cutoff. It's a little bit lower. And then voltage swing, since our maximum input is 5 volts. And here we have 4 point something positive, and then negative 4 point something on the negative side. Apparently our positive side is very close to 4. Our negative side is closer to 5. So that's all for my presentation. Thank you for watching it.